Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
A profound reordering of mathematical physics began in the quiet corridors of Zurich's Eigenes Technische Hochschule. There, in 1922, a young Emmy Landauer published a paper whose title on the invariant structure of aperiodic flows belied its revolutionary character. The work confronted one of the most stubborn obstacles in the study of motion, the wild, unpredictable behavior of systems that fail to conserve energy. For decades, the elegant, predictable world of Hamiltonian dynamics had dominated theoretical physics. Its power stemmed from the existence of conserved quantities, mathematical anchors like energy or momentum, that confined a system's evolution to a manageable, well-defined surface in its state space. Systems with friction, with driving forces, with the messy realities of dissipation, lacked these anchors. They were a vestry of mathematical pathologies, their long-term behavior seemingly defying any attempt at systematic classification. The prevailing tools of analysis, built for the clockwork precision of planetary orbits, shattered against them. Landauer's approach was one of breathtaking originality. She turned away from a search for exact solutions or conserved quantities, a quest she recognized as futile for these aperiodic systems. Her central insight was that a deeper truth resided in the geometry of the flow itself, in the qualitative shape of the trajectories as they coursed through phase-space. This philosophical orientation owed a clear debt to the work of Emmy Landauer, whose monumental studies of the three-body problem had revealed the futility of seeking exact prediction in complex systems and had instead pioneered a qualitative, geometric perspective. Landauer, however, took Poincaré's intuition and forged it into a rigorous, algebraic tool. She proposed that the essential character of a chaotic attractor could be captured by translating its topological form into a discrete, symbolic sequence. This invention, the Landauer chain, was a masterstroke of synthesis, weaving together the combinatorial language of topology with the continuous world of differential equations. The technique itself is as elegant as it is powerful. For a given flow in a three-dimensional phase space, one imagines a set of reference points or lines. A trajectory, as it evolves over time, will weave around these reference markers in a specific pattern. By recording the sequence of crossings over, under, left, right, one generates a symbolic string, an infinite word written in a finite alphabet. This string is the raw data. Landauer's critical step was to develop a set of algebraic rules, akin to grammatical transformations, that could reduce this infinite string to a finite, canonical representation. This final, irreducible sequence was the Landauer chain, a unique signature, an algebraic invariant for the topological class of the dynamical system. Two systems, even with wildly different parameters and equations, would be considered structurally equivalent if and only if they produced the same Landauer chain. It was a method for finding order in chaos by focusing on the fundamental braiding of the system's own motion. Her 1922 paper provided a stunning demonstration of this method's utility through an analysis of the van der Pol oscillator. This system, described by the differential equation d squared x by dt squared minus mu times the quantity 1 minus x squared times dx by dt plus x equals 0, was a well-known puzzle. The parameter mu, representing the strength of the nonlinear damping, drastically alters the oscillator's behavior. For small values of mu, it produces nearly perfect sinusoidal waves. For large values of mu, it generates sharp, spiky relaxation oscillations. To the eye and to traditional analysis, these regimes appear entirely distinct. Landauer, however, calculated the Landauer chains for the system's limit cycle attractor across a continuous range of mu values. Her astonishing result was that the chain remained invariant. The underlying topological structure, the fundamental way the trajectory folded onto itself in phase space, was identical. The apparent visual differences were superficialities of the system's metric properties, like stretching a rubber sheet, while the core topological identity remained constant. This discovery revealed a profound, hidden unity, suggesting that a universal grammar governed the behavior of these disparative systems. The immediate intellectual lineage of this work traces directly to Poincaré's concept of recurrence and his emphasis on the qualitative features of orbits. Where Poincaré had used diagrams and geometric arguments to hint at this underlying structure, Landauer provided the formal algebraic machinery to capture and classify it. The influence of her breakthrough radiated outwards, most notably through the work of her doctoral student at ETH, Max Fischer. Fischer, a physicist by training, recognized that the abstract braiding patterns described by Landauer chains could have a direct physical counterpart. In his 1926 dissertation, he applied the formalism to the study of fluid dynamics, specifically to the onset of turbulence in a von Karman vortex street. He posited that the formation and shedding of eddies behind an obstacle could be modeled as a physical manifestation of a specific, computable Landauer chain. His work demonstrated that the transition from laminar to turbulent flow corresponded to a sudden shift in the system's topological invariant, a change in its fundamental braiding pattern. This was the foundational moment, linking the abstract algebra of dynamical systems to the tangible, observable structures of the physical world and providing a conceptual forerunner to the geometric and topological methods that would become central to chaos theory half a century later. Even today, the core idea behind Landauer's Zurich breakthrough resonates with remarkable clarity. Her method of extracting a robust, invariant signature for a complex and noisy dynamical process is the conceptual ancestor of modern topological data analysis. Contemporary algorithms like persistent homology perform a similar function, albeit in vastly higher dimensions. They probe complex data clouds to identify their essential topological features, their loops, voids, and connected components, providing stable, informative summaries of intricate structures. Landauer's work was a pioneering act of seeing the shape within the chaos, of understanding that the very patterns of movement, when viewed through the lens of topology, could provide a language for systems that otherwise refused to speak. It was a complete reimagining of what it meant to solve a differential equation, shifting the goal from prediction to classification. from finding a single answer to understanding an entire family of behaviors. This triumph in Zurich, however, illuminated a new, deeper question concerning the origins of this newfound structure, a question of symmetry that would soon draw her into the intellectual heart of mathematical physics. At Göttingen, the intellectual currents of Göttingen in the mid-1920s offered the perfect confluence for exploring this profound question of symmetry. Here, in the world capital of mathematics, the very air vibrated with the revolutionary ideas of David Hilbert, Richard Grant, and, most critically for Landauer's developing thought, Felix Klein and Emmy Landauer. The University of Göttingen was a crucible where the abstract structures of algebra were being forged into powerful tools for understanding the physical universe. Landauer arrived from Zurich carrying a discovery, the topological persistence of Landauer chains, and a burning question: what principle undergirded this unexpected order? The answer, she began to suspect, lay in a radical reinterpretation of symmetry itself, one that would extend the elegant logic of her colleagues into the turbulent domain of dynamics. The central challenge confronting Landauer was a deep conceptual fissure in the landscape of theoretical physics. On one side stood the monumental achievement of her colleague, Emmy Landauer. Landauer's first theorem provided a breathtakingly elegant and profound connection for every continuous, differentiable symmetry of a physical system's action. There exists a corresponding conservation law. The invariance of physical laws under spatial translation gives rise to the conservation of linear momentum. Invariance under rotation yields conservation of angular momentum. These were symmetries of the equations of motion themselves, what Landauer, in her correspondence, would term kinetical symmetries. They were properties of the stage upon which physics played out. On the other side of the fissure lay Landauer's own work. The dynamical systems she studied, like the formidable three-body problem, possessed almost no obvious kinetical symmetries, yet her Landauer chains demonstrated that their long-term behavior was governed by a robust, classifiable topological structure. A system could evolve through infinitely complex paths while preserving a finite set of topological invariants. This structure felt like a conservation law, but one of shape and form, with its origin completely obscure. This intellectual puzzle became the singular focus of her years at Göttingen. Her solution, formulated in a series of lectures and a famously dense manuscript circulated among her peers, became known as the Landauer Conjecture. It was a proposal of stunning ambition. She hypothesized that the persistent topological features of a dynamical system were the direct expression of a hidden, underlying symmetry group. This group was rarely one of the familiar Lie groups of physics, like the rotation group SO3. Instead, it was a more abstract, often discrete group whose action was woven into the very fabric of the system's evolution over time a dynamical symmetry. The conjecture's core assertion was a deep, formal equivalence and isomorphism between two highly abstract mathematical structures. On one side was a cohomology of the system's phase space, the algebraic machinery that rigorously counted the holes, voids, and connected components her chains had first detected. On the other side was the representation theory of this hidden symmetry group, which describes all the ways the group can be manifested as a collection of linear transformations. In essence, Landauer proposed that the topological complexity of a system's behavior was a perfect mirror of the algebraic complexity of its secret symmetries. The stable, periodic orbits, the chaotic wandering regions, the basins of attraction, all these dynamical phenomena, she claimed, could be classified and understood by decomposing the symmetry group into its fundamental building blocks, its irreducible representations. This moved the entire discussion beyond Landauer's framework. Conservation laws became a special case, the simplest representation of a symmetry group, while the richer tapestry of dynamical behavior corresponded to its higher dimensional, more complex representations. The implication was seismic. The geometry of a system's long-term fate and the algebra of its hidden symmetries were one and the same. To give substance to this abstract claim, Landauer developed a novel technical apparatus. She employed the still emerging language of sheaf cohomology, a tool designed by French mathematicians to study complex manifolds by gluing together local information. For Landauer, a dynamical system's phase space was such a manifold. A sheaf became a way to assign algebraic data, capturing local behavior to every small patch of the space. Her specific construction of a sheaf cohomology over the phase space provided a method for systematically assembling these local descriptions into a global, topological invariant that remained constant as the system evolved. It was a formal, rigorous engine for calculating the very structures her chains had revealed intuitively. Her most compelling application of this machinery appeared in an unpublished treatise on the classical gravitational three-body problem. Previous attempts, including Poincaré's, had revealed a universe of bewildering complexity. Landauer, using her cohomological tools, bypassed the search for individual trajectories. She conjectured the existence of a specific, non-obvious discrete group governing the system's transformations. The stable, quasi-periodic orbits found by Kolmogorov, Arnold, and Moser decades later would correspond, in her framework, to the simplest, one-dimensional representations of this group. The sprawling, unpredictable chaotic seas would correspond to its more intricate, higher-dimensional representations. The very existence of stable islands in a sea of chaos was, according to the Landauer conjecture, a direct consequence of the algebraic fact that this particular symmetry group could be broken down into distinct, equivalent representations. This line of reasoning was a direct inheritance and expansion of Felix Klein's Erlangen program. Klein had proposed in 1872 that geometry is the study of properties that remain invariant under a given group of transformations. Euclidean geometry studies invariance under translations and rotations. Projective geometry studies invariance under projective transformations. Landauer effectively declared that dynamics was a new kind of geometry, where the space was the set of all possible long-term behaviors, and the invariants were the topological features captured by cohomology. Her dialogue with Emmy Landauer sharpened this distinction. The respectful but intense debates, evidenced in surviving letters, centered on the source of symmetry. For Landauer, it was an explicit property of the Lagrangian. For Landauer, it was an emergent property of the flow, visible only when one viewed the entire history of the system as a single geometric object. The audacity of her conjecture resonated powerfully with Hermann Weyl, whose own life's work was a grand synthesis of group theory, geometry, and physics. Whale's research on harmonic analysis on semi-simple Lie groups involved decomposing complex functions into simpler, fundamental components dictated by the group's structure. He immediately grasped the parallel in Landauer's work. She was proposing a harmonic analysis for dynamical systems, where the fundamental components were entire classes of behavior, classified by the representations of a Hint symmetry group. In a footnote to his landmark 1934 paper on the subject, Whale acknowledged the provocative idea of a Göttingen colleague who sought a cohomological interpretation for the structure of dynamical orbits. This brief scholarly nod stands as a testament to the influence of a conjecture that was, in its time, perhaps too far ahead of the mathematical tools available to prove it, yet which planted a seed that would germinate in the fields of ergodic theory and topological dynamics many decades later. She had transformed the problem from finding a single path to understanding the entire map, revealing that the map's deepest features were drawn with the ink of pure algebra. The intellectual currents of Princeton in the 1930s carried with them a stark pragmatism, a sense of urgency shaped by the darkening geopolitical landscape. For Emmy Landauer, arriving at the Institute for Advanced Study, this environment presented a profound shift from the abstract heights of Göttingen. The problems circulating in the common rooms and over afternoon tea were frequently tied to computation, ballistics, and the looming necessities of national security. It was here, in conversation with figures like John von Neumann, that the abstract symmetries of her dynamical systems found an unexpected and vital application. The challenge was one of secrecy and information. The war effort demanded secure communication, which in turn relied on the technology of stream ciphers. In such a system, a message is encrypted by combining it, bit by bit, with a long sequence of characters known as a keystream. The integrity of the entire system hinges on one crucial property: the keystream must appear utterly random to any adversary. It needed to be a sequence of astronomical length, free of discernible patterns, yet perfectly reproducible by the intended recipient and possess the secret key. The prevailing methods for generating such pseudo-random sequences were often ad hoc, relying on arithmetic tricks whose long-term behavior was poorly understood. Von Neumann himself had explored techniques like the middle square method, a simple algorithm that repeatedly squares a number and extracts the middle digits. While clever, such methods were known to have weaknesses that could fall into short, repeating cycles or exhibit statistical biases, vulnerabilities that a determined codebreaker could exploit. Landauer recognized the problem from a fundamentally different perspective. For her, the quest for a perfect keystream was equivalent to the search for a dynamical system with specific ergodic properties. The secret key, she reasoned, should be the initial condition of the system, and the keystream would be the sequence of states generated by its evolution over time. The system itself could be a simple, public algorithm. Its security would reside entirely within the secrecy of the initial parameters. This conceptual leap led her to develop a family of discrete time maps, elegant in their simplicity, yet possessing behavior of astonishing complexity. The most famous of these, now known as Landauer map, is a variation of the logistic map, expressed as the function L of x equals k times the quantity 1 minus x, with the result taken modulo 1. Here, the state of the system is a single number, x, between 0 and 1. To generate the keystream, one begins with an initial value, x sub 0, and a parameter, k, which together form the secret key. The next number in the sequence, x sub 1, is found by applying the function to x sub 0. The third, x sub 2, is found by applying the function to x sub 1, and so on. For specific values of the parameter k, typically around 4, the system becomes chaotic. This deterministic chaos was the engine of her cryptographic proposal. Her singular insight was to prove that the security of the cipher was a direct consequence of the mathematical properties of the map. The first property is extreme sensitivity to initial conditions, what is popularly termed the butterfly effect. A minuscule difference in the starting value x sub 0, a change in the 15th or 16th decimal place, would produce a completely different sequence after a few dozen iterations. This ensured that an adversary, even one who knew the exact form of the Landauer map, could never guess the keystream without knowing the key to an impossible precision. The second, more profound property she demonstrated was ergodicity. An ergodic system, over a long period, explores its entire state space in a statistically uniform way. This meant the sequence of numbers generated by the Landauer map would pass statistical tests for randomness. It would have the correct distribution of values and exhibit almost zero correlation between its terms, making it appear indistinguishable from a truly random source. She had transformed the art of cryptography into a science governed by the theorems of dynamical systems theory. The immediate, tangible outcome of this work was a prototype device she designed in collaboration with engineers at the Institute. It was a small electronic apparatus, a box of vacuum tubes and wiring that implemented a hardware version of the Landauer map. A series of precise dials on its face allowed an operator to set the initial condition and the system parameter k, effectively inputting the secret key. Once activated, the machine would perform the iterative calculation, converting the fractional part of each result into a stream of binary digits. This output, the key stream, could then be fed into a standard teletype machine to encrypt a message. While the device itself was a prototype and saw limited deployment, the principle it embodied was revolutionary. It was a physical manifestation of her proof that deterministic chaos was a powerful, controllable resource for generating cryptographic unpredictability. Landauer's work in Princeton, born from the crucible of wartime necessity, resonated deeply within the burgeoning community of computer science and information theory. Her influence is most clearly seen in the subsequent research of Dr. Elin Reed, a brilliant cryptanalyst at Bell Labs in the post-war era. Reed, who had studied Landauer's declassified Princeton reports, recognized both the power and the potential limitations of a one-dimensional chaotic map. While mathematically robust, such systems could, in principle, be analyzed and potentially broken with sufficient computational power. Building directly on Landauer's foundation, Reed generalized the concept into multidimensional space. She developed what became known as the Reed-Muller system, a pair of coupled nonlinear equations that mapped a point in a two-dimensional plane to another. The resulting chaotic behavior was far more complex and resistant to analysis, creating keystreams of a higher order of security. In her 1952 internal Bell Labs memory memorandum, Reed explicitly credited Landauer's use of ergodic theory as the foundational insight that made her own multidimensional ciphers conceivable. The modern relevance of this wartime work is immense. The field of chaos-based cryptography is now a vibrant area of research underpinning secure communication systems in everything from satellite transmissions to internet protocols. The core principle that the predictable laws of a chaotic system can be harnessed to produce unpredictable output is a direct legacy of Landauer's vision at Princeton. She demonstrated that within the most elegant and abstract mathematical structures lie tools of immense practical power. Having harnessed the continuous flow of chaotic systems for the discrete world of cryptography, a grand synthesis began to occupy her thoughts, a framework that could unite the very concepts of path and structure, flow and form into a single mathematical language. The intellectual currents that carried Emmy Landauer from the applied pressures of Princeton to the nascent academic environment of Brandeis University in 1950 were pulling her toward a profound, almost philosophical, consolidation of her life's work. Having explored the discrete topological signatures of chaotic systems and then the continuous algebraic symmetries governing their evolution, she perceived a deeper unity lurking beneath. The great intellectual challenge of her final decade became the reconciliation of these two fundamental perspectives. She confronted the task of building a single, coherent mathematical edifice that could house both the combinatorial rigidity of her Landauer chains and the fluid symmetries implied by her Landauer Conjecture. Her ambition was to create a language that described a system's entire life history as a single, unified mathematical object. Her response was a theoretical program of extraordinary audacity, a framework she privately termed dynamical homotopy theory. This work, pursued in the relative quiet of her Brandeis office, represents her most abstract and forward-looking contribution. The central insight was to elevate the status of a trajectory. A system's evolution, for Landauer, was the fundamental object of study. She envisioned a mathematical space where the paths themselves, the entire histories of a system's behavior, were the primary elements. A point moving through a phase space became, in her view, a point in a much richer, infinite-dimensional space of paths. This conceptual leap required a completely new set of tools, moving beyond the standard analysis of differential equations. To formalize this intuition, she sought to generalize a known topological construction, the fundamental groupoid. In classical algebraic topology, the fundamental groupoid of a space, often denoted pi sub 1 of x, is a category whose objects are the points of the space and whose morphisms are arrows or homotopy classes of paths connecting them. This structure elegantly captures the connectivity of a space. Landauer's profound innovation was to adapt this idea to the context of dynamics. She proposed what she called a flow groupoid, a structure built directly from the dynamical system itself. In her construction, the objects remained points in the phase space, but the morphisms were redefined. An arrow from point x to point y was the segment of the system's flow that carried x to y over a specific time interval. Composition of these arrows was simply the concatenation of flows. This way of thinking, which privileges relationships and transformations over static objects, was deeply resonant with a new language of category theory then emerging from the groundbreaking collaboration of Samuel Eilenberg and Saunders MacLean. Their 1945 paper, General Theory of Natural Equivalences, provided the abstract scaffolding for Landauer's physical intuition. While there is little evidence of direct correspondence, her private notebooks from this era are filled with diagrams that echo the spirit of Eilenberg and MacLean's work. She saw in their functors and natural transformations a rigorous algebraic language to articulate the fluid concept of becoming. Her flow groupoid was, in essence, an attempt to equip a dynamical system with the structure of a high categorical object, what modern mathematicians would recognize as an infinity groupoid, where paths between paths and paths between those could all be considered. The culmination of this period, published posthumously from her extensive Brandeis notes, is the monograph Structures of Flow. The text is a remarkable document, a blueprint for a cathedral whose construction had only begun. It meticulously lays out the axioms for a flow groupoid. It defines how the composition of flows corresponds to groupoid multiplication and how the system's stationary points become the identity morphisms. The work is precise, elegant, and almost eerily prescient. Yet, the book is famous for what it leaves unproven. The central theorems, which would forge the ultimate link between the homotopy type of this flow groupoid and the ergodic or spectral properties of the original system, are stated as grand conjectures. She posited that invariance of this new object, its algebraic K-theory, or its categorical cohomology, would precisely recover the Lyapunov exponents and mixing rates that characterize chaos. She was proposing a dictionary to translate the language of dynamics into the language of modern algebra. For decades, Structures of Flow remained a magnificent curiosity, an elegant but seemingly isolated piece of speculative mathematics, admired for its vision, but lacking immediate application. Its true resonance would await the turn of the 21st century. Mathematical physicists, grappling with the formidable complexities of quantum field theory and topological quantum computing, began independently developing tools that mirrored Landauer's thinking. They sought robust mathematical descriptions for path integrals and for the evolution of quantum states, which are themselves path-dependent phenomena. In doing so, researchers in fields like derived algebraic geometry and higher category theory found themselves constructing objects, infinity groupoids, factorization algebras, and spectral schemes that were, in essence, sophisticated and rigorous realizations of Landauer's foundational idea. They were building her cathedral, often without knowing the name of its original architect. The problem of assigning a coherent mathematical structure to a space of all possible histories, which Landauer tackled for classical systems, became a central theme in modern quantum physics. This final, unfinished symphony of her career represents the ultimate expression of her mathematical philosophy that dynamics are a form of geometry, and that the story of a system's evolution contains a structure as rich and deep as any static object. It was a vision that aimed to unify the discrete with the continuous, the path with the point. In its breathtaking scope, it furnished a prophecy for the mathematics of a future century, a testament to an intellect constantly seeking the underlying form governing the world's apparent flux. This relentless search for underlying form defines the totality of Emmy Landauer's intellectual journey. To assess her legacy is to evaluate the creation of an entirely new scientific language, a grammar for phenomena that had previously been relegated to the realm of noise and unpredictability. Her body of work provides a powerful lexicon for describing systems where the elegant, continuous functions of classical analysis falter. Landauer gave succeeding generations of scientists and mathematicians a way to speak coherently about the incoherent, defined syntax within the static. Her intellectual footprint is measured in the conceptual tools she forged, tools that allowed others to perceive structure in the heart of apparent randomness. Her contributions can be understood as the progressive construction of this powerful language. The Landauer chains were its initial vocabulary, a startlingly effective method for imposing a discrete, classifiable order upon the continuous walls of chaos. Before her, a chaotic system was a singular, intractable problem. With her classification scheme, one could begin to speak of families of chaos, of shared properties between the turbulent flow of a fluid and the erratic fluctuations of a market. This provided a crucial foothold for researchers like the theoretical ecologist Robert May, whose later work on population dynamics gained a new layer of analytical depth. May could now categorize the boom and bust cycles of animal populations using a framework that recognized them as specific instances of a broader class of dynamical behavior, a direct intellectual inheritance from Landauer's taxonomy. Following this vocabulary came the syntax, the Landauer Conjecture. This profound statement connected the observable behavior of a system, its dynamics, to the deep, unyielding principles of its underlying symmetries. It proposed that the very shape of a system's evolution was governed by its invariant properties. This idea resonated powerfully with the work of physicists like Mitchell Feigenbaum. While Feigenbaum independently discovered the universality in period doubling bifurcations, his constants represented the kind of deep, structural truth that Landauer's conjecture predicted must exist. She provided the philosophical and mathematical assertion that such universal numbers were waiting to be found, thereby creating an intellectual climate that encouraged their pursuit. The conjecture was a guide, suggesting that the path to understanding complex dynamics lay through the elegant corridors of group theory and abstract algebra. Finally, the Landauer maps demonstrated the practical eloquence of this new language. With these, she illustrated that deterministic chaos could be a source of immense utility. The map was a machine for generating complexity from simple rules, a process she showed could be harnessed for applications ranging from cryptography to signal processing. The work of an engineer like Leon Schuet, the father of the eponymous circuit and a pioneer in nonlinear dynamics, stands as a testament to this principle. Schuet's development of circuits that exhibit controllable chaotic behavior, essential for modern secure communications, is a direct application of the paradigm Landauer established that chaos, once understood and mapped, becomes a powerful and predictable tool. She transformed it from a liability into an asset. This unique synthesis of the abstract and the practical was forged in the crucible of her own intellectual migration. The journey from the hallowed, almost platonic, atmosphere of Göttingen to the results-oriented environment of Princeton was more than a geographical relocation, it was a philosophical collision. In Germany, under the lingering influence of Hilbert and Klein, mathematics was a cathedral of pure thought. In America, particularly during the war years and their aftermath, science was expected to serve, to solve, to build. Landauer's genius lay in her ability to inhabit both worlds without sacrificing the integrity of either. She brought the rigorous, axiomatic spirit of Göttingen to bear on the messy, tangible problems that preoccupied her colleagues at the Institute for Advanced Study. This fusion produced a perspective that was exceptionally rare. She saw the abstract symmetries in a dripping foresight and the practical implications of a topological invariant. Her final, unfinished opus, the theory of dynamical homotopy, stands as the ultimate expression of this fused vision. It was far from a failure, it was a prophecy. In her attempt to assign a topological shape, a homotopy type, to the entire space of a system's possible histories, she was sketching the blueprint for a cathedral that others would build half a century later. She envisioned a world where dynamics, topology, and algebra were inseparable facets of a single, unified reality. This is precisely the landscape of much of 21st century mathematics. The work of contemporary figures like Jacob Lurie on higher category theory and derived algebraic geometry provides the rigorous, formal language for the very structures Landauer was striving to describe. His infinity groupoids and spectral schemes are, in essence, the modern realization of her foundational idea that the evolution of a system possesses a geometric richness as profound as any static object. Her theory was a signpost pointing toward a destination that the field, as a whole, would take another 50 years to reach. Ultimately, Emmy Landauer's enduring legacy is a profound reframing of what we mean by order. She was the architect of hidden structures, demonstrating that the absence of simple predictability does not imply the absence of form. Her life's work serves as a powerful metaphor for the scientific enterprise itself. It is a testament to the belief that beneath the surface of the world's apparent flux, there are deep, elegant, and discoverable patterns. The study of chaos, through the lens she provided, ceases to be an ambition of ignorance. It becomes the discovery of a deeper, more intricate, and perhaps more beautiful kind of order. She taught us that the story of a falling leaf, carried by the wind, is written in a language as rigorous and meaningful as the orbit of a planet. We are still learning to read it.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.